It's a bit rude. So I want to just go through some of these points, which are basically basic geological principles. I don't remember where all the photographs are, because a lot of them came from Chris, so I have little notes about what the different pictures are. This is a guy trying to collect a core from a kayak, which it doesn't look like it. It looks like a proper kayak, sort of one that you, well, oh, maybe it's a canoe. But anyway, it doesn't look like it's something that's that stable. So he's trying to collect a marine core or a lake core, perhaps, by inserting this tube into the sediments and extracting. I think it's slightly mad because I'm slightly scared of kayaks, and I'm convinced I'll get stuck upside down. I like to sit on top kayaks because you can jump off this, don't drown. This picture here is just showing a whole lot of pile of rubbish and bits of debris and stones that you find on a beach. And that's just to show that all these different things have totally different histories. They've gone through different paths through the Earth's surface system, and yet they've all ended up in the same place, all being deposited. And that's the sort of evidence that we use on a more microscopic scale, really. We don't find, not quite like this, bits of plastic and seaweed and dead fish skeletons and stones, but we look at these kind of bits of evidence, biological sedimentary evidence, to work out past climate. So superposition first. Superposition, you know how good I am at saying long words, I often get quite confused. For years I thought this was was supposition. And for years I taught about supposition until somebody said that just doesn't make any sense. So this is superposition, which when you think about the word makes a lot more sense. It's about the position of the sediment, one on top of the other. So the law of superposition, which I can't say very well, basically states that the older sediments are at the bottom, and as they go on top, sediments deposited on top or rocks on top will be younger than the one below. And these are argued rather similar or related to geological concepts, showing that that you'll expect lateral continuity. So if you were to take two cores through a peat bog fairly close together, you would hope that they would have the same kind of sequence, even if you had a stream channel or something cutting through the peat bog. This idea that originally sequences were placed horizontally, and that if you have something cross-cutting through other layers, then that must be younger than the layers that it's cutting through. But the one that we're particularly interested in is this, and to some extent lateral continuity. Because a lot of the records that you've been looking at are taken from hundreds, if not thousands of miles apart, so this doesn't really apply. But we usually assume, unless we have some more information about reworking or some other processes that have gone on in the sedimentary record, that the lower down the coral you go, the older things are, which is probably not really supposed to be. So this is the one about the fish skeleton and bits of plastic and stones. The idea of equifinality, that to get a degree, you can get there through many paths. You can have gone straight from school or college, got A-levels, gone and do a 3-year degree, not change your mind about what you want to do halfway through, get outstanding marks all the way and get first. Or you can go through a series of other processes, go off and do year award or something, and then come do the same thing. Or you can spend 40 years working, making boxes in a factory, and then decide to do an access course and get a degree as well. Or you can come in, do absolutely nothing in your first year, almost fail, still quite wait your way to second year, and start working really hard and still get a first-class degree. So there's lots of different ways of getting a first-class degree. And the same, there's lots of different ways to placing a sediment or getting something into a particular spot in a core. You can have travelled through different pathways, through the oceans, through the atmosphere, through across the land. It can have been passed through animals. It can have many ways to get something to the same location. And also many ways to create the same type of sedimentary sequence, yet actually you can't take a sedimentary sequence and assume it means one exact thing, because you couldn't get the same pattern of sediments produced reproduce in a variety of ways. The problem I have with Teflon, because it's often reworking and compaction of sediments, means that many different processes, volcanic processes, end up looking the same as sedimentary record. But we're not here to talk about volcanoes, I'm not allowed to, so I get to do that tomorrow afternoon. I think I've got that. Okay, taphonomy is basically about making fossils. So taphonomy is just the word used to say how material is preserved, how particularly biological material is preserved. You probably won't encounter the word very much. It goes to the point of basically a creature living, then it dying, it being buried or being exposed to various different processes, then turning into a rock and being caught in a fossil record, or being preserved and being found in a sediment core, which is more the sort of thing we're talking about. You don't really need to know the term for death in fossils. Diagenesis is kind of useful to know because it's about transformation of sediments into rocks, but again, that's on probably a longer time scale than we're talking about, because mostly we're looking at quaternary records, where everything's still fluid. But taphonomy is a useful word to know. And actually, for something to make it from being alive to being in a fossil record or to being in a sediment core, somewhere along the line, all these things need to have happened, and it can't have been disturbed by anything. So that means that if a little creature dies, falls to the bottom of the sea, for it to be in our sediment core, it has to be not eaten by anything else. It hasn't been picked up by current and moved somewhere else. Or if it has, if you think about the fact what we see in the sediment core didn't necessarily live in the water column directly above the sediment core. And so there's a variety of ways, at least for marine records, but also terrestrial and icicle records, you can interrupt this so not everything that lives gets trapped in sediments. Okay, so there are four main types of sedimentary archives, and we're going to particularly look at two of them. So heterogeneous, biogenic, orthogenic, cosmogenic, and I'll explain what all of those are. But these are the two that we're mostly interested in. So heterogeneous means, you think of the word terra, and geneos mean to do like genetics or how it's produced. Material that has come from the land and deposited offshore. So as we're looking at marine records. So for example, this mostly relates to rivers. So I have it written to here, about 62% of the deep ocean floor, oh no, this is real. So that's the next one, I'm ahead of myself, sorry. Most of the material that comes from heterogeneous material that ends up in the ocean has been transported from rivers off the land into the sea. Probably doesn't surprise you very much. This is the 62% of deep ocean floor. So 62% of the deep ocean floor is covered in biogenic material. And there's basically two types of biogenic material that's relevant to this, or relevant to this module. We look at evidence as calcium carbonate. This is the distribution of calcium carbonate in the ocean, on the ocean floor. You see that quite a lot of the ocean floor has got more than 70% of it made up of calcium carbonate. Calcium carbonate has been in the skeletons of creatures, and then they fall to the bottom of the ocean floor. So it's quite significant. It's sometimes described as carbonate ooze, presumably because it's a muddy, sludgy sort of mess. And then the other sort of biogenic evidence that we're interested in is silicious or silica-rich biogenic silica. And certain creatures trap silica in their system when that's preserved. So basically only the sort of bits, the fleshy bits of animals and plants, they don't survive, do they? So it's just like fossils, just like dinosaur bones. It's the bits that are really, really resistant to erosion or to being eaten by other things are the bits that are preserved. So calcium carbonate and silica. So here we can see that silica is mostly on the land, but also around the Arctic Ocean. There's not quite so widespread as calcium carbonate remains. It needs to be something that's going to survive reworking and being eaten and rotting. So orthogenic, which we don't really need to worry about too much, is associated with deposition in marine records because of falling out of suspension, falling out of the water column onto the ground, or recrystallization in situ. So, but the point is about orthogenic is it's not, orthogenic material hasn't been transported from somewhere else. So if material travels on ocean current, then it's not orthogenic. It's only where it's actually placed in situ. Much of what we're looking at is actually has been moved around. And cosmogenic is basically material can get into marine records through cosmogenic particles. So basically meteorites, bits of meteorites falling into the oceans. This is a really tiny fraction of sediment in the marine records. So we're not going to really particularly take any more notice of that at the moment. So as I said, we mostly rely on heterogeneous material, that's land-based material, or biogenic material. So I'm going to talk a little bit about these. Okay. Some of you asked me, or asked Chris, what IRD is, because you had encountered that in one of the data sets that you got from, you downloaded from the websites for your first practical. Well, these relate to IRD. This is actually IRD, it's ice rafted debris. These are quartz grains. And this is how it gets there. So, coming off the Laurentide ice sheet when it was really big, covering North America, blocks of ice would break off the front of the ice sheet, and those ice blocks were full of sediment that had been trapped in the ice in the glacier, and that would come from North American landmass, as in sort of transported by streams over the ice, through the ice,